Hello, is that working? Good. So hi, my name is Oliver. I want to talk to you tonight about functors, apply, applicative, and monads. So this is the talk that I kind of wish I got given when I first started functional programming. Because these people were walking around, talking around functors, monads, and all these different words, and I didn't have a clue what was going on. So I wish that someone had sat me down and explained these things to me. Sorry, let's turn this on. There we go, that's better. So I guess those words were just plain dull for me. So let's try this instead. Rescuing Princess Purity from castle side effects. So why should you care? At the end of the day, there's these functional concepts, and like, how do they help you deliver decent software? We get paid to go to work every day and pump this stuff out, and sometimes you can get lost in kind of the intricacies of how you're trying to do that. So whilst I'm doing this talk, I want you to there's three concepts which kind of I want you to think about. So first, a couple of questions. They're pretty easy. If a pizza costs $16 and you buy two, how much do you spend? Don't shout out the answers. It's pretty easy. So if you hire a Mario Kart for $20 a day and you rent it for 2 days, how much do you spend? The point is not to think about the maths. Think about the process that you're going through. What information you're losing and what information you're keeping. So this is abstraction. We're taking, with this picture, we all know that this is a houses, and you can see some people there standing, having a nice walk and stuff. But it looks nothing like a house that we've seen before. But we all know that that is a cityscape. So this is the process of abstraction. Abstraction is the emphasis on the idea, the qualities, and the properties, rather than the particulars. And the importance of abstraction is it hides irrelevant detail, so we can focus on exactly what we're trying to solve. So it doesn't matter if it's pizza or Mario Kart. What it matters is we take the two values and we multiply it by a number. So we get rid of the pizza and the Mario Kart in both situations. The second concept I want to think about is this. So what's the relationship between a polygon and a three-sided triangle or a four-sided quadrilateral? So this equation here, what's this got to do with these two equations down here? This concept is something which we do every day in our lives as software developers. It's generalization. We extend classes, we write interfaces, and we have this concept of generalization. So these concepts of abstraction and generalization are things that we as software developers use every day. The final concept is this. Is a mile a long way? Or is a year a long amount of time? It all depends on your context. It depends where you are and what you're doing at that point in time to whether it's important or not. So to an ant, a mile's a long way. It's going to take him a long time to walk a mile. But if you're traveling in an aeroplane, you go very quickly. A year is a long time for something like an animal like a mayfly that only lives for about 3 hours or 24 hours. But for a rock, it's a really long time. Okay, so those three concepts are what I want to think about whilst we're talking to it. So let's get everyone up to the same level, because there's probably people here who haven't done much functional programming before, so I'm just going to try and get you all up to about the same level. All right, functional programming. We construct our programs using only pure functions, and pure functions have no side effects. Now, this is really important, having no side effects. You can think about our functions being a bit like a pipe. Seeing as we're doing Mario, we talk a lot about pipes. You put something in one end, and out pops something at the other end. We can then take those pipes and put them all together, and we can build really complex systems like this. And if we want to figure out how a bit of that system works, we take that pipe out and we test it. And we can test it in isolation because it's not leaking, it's not causing any problems. And then we can put it back into place, and it works as part of the bigger system. So we can build complex systems out of these small parts that we can reason about. Like I said, what's so good to reason about? What's good about no side effects is that we can reason about it. We can know how these things act and when we put them together. And this is what happens when we have side effects. You can see here that all the side effects are leaking out. It's hard to reason about on. You don't know which threads are talking to which variables or mutating which things or changing things on the file system. So it makes it a lot harder to reason about. So that's why we want no side effects. All right, so now we go. Ready to go into level 1. So Mario is going to go into level 1 in Functor land. And the first baddie he comes across is a GOOMBA. So this bad guy, he needs to get stomped by Mario, and if Mario stomps him, he pops out a coin. So how to defeat a GOOMBA? We've got here a case class coin, a case class GOOMBA, and we stomp him by passing the GOOMBA in and getting back the coin. So the function stomp is our pipe, and we get back the coin. So Mario's got a friend called Luigi, and Luigi invents this vacuum cleaner, which can pick up the GOOMBAs and stomp him. So we create a class for the vacuum cleaner, and we put the stomp function on it. We create a new vacuum, we create a GOOMBA, and we suck up the GOOMBA, and we get a coin out. Unfortunately, sometimes when they're using this vacuum, it escapes. So the function which we're getting this GOOMBA from is unreliable. Sometimes it gives us back a null pointer. So what happens when we do that? Everything explodes. We get a null pointer, the system stops working. So what's the solution to this? The solution is we can check for nulls. So in the Java code, you can do a null check. But this isn't very nice. This is just passing that null pointer back out to your client and polluting their code as well. At some point, someone's not going to check that null pointer, and your code is going to blow up. So there must be a better way. There must be a simpler way of solving this problem. So our simple solution is to put the GOOMBA in a cage. Therefore, we know what we're going to get. We know we're always going to get a cage of some form, and we can look in that cage, and we can say, is it empty or is it full? So here's this in code. We've got a cage trait, which is parameterized by type T. And that has a full cage, which extends type cage. And we have an empty cage, which extends type cage as well. And we have a way of constructing that object using apply. Here's how we use it. So into the cage, into the collector, we get a cage. If it's an empty cage, we do a pattern match on it, and we get back an empty cage. And if it's a full cage, we apply the stomp function, and we send back the full cage. So now, we run the vacuum, and it works, and we get back a full cage with a coin. And if we we try and collect a cage which is empty, then we get back an empty cage. So no more boom boom. Can we generalize a vacuum class? So they've got this idea now, and we want to now generalize it. So we want to lift that up, and we want to generalize that across the problem. Why just limit ourselves to stomping GOOMBAs in the cage? So here what we've got is we've got a vacuum. We've got a cage which is filled with type A. We've got a function which takes us from f of A, which takes us from A to B. And if we have an empty cage, we can just send back an empty cage. If we have a full cage, we take what's in the cage, we apply a function, and return back a cage. So now we've got a cage which can hold any type, and a function which convert from type A to type B. To generalize even more, we can turn it into a trait. So now we create an interface which other things can implement. So the code's the same. We've just extracted the function out into an interface, so we can have different types of vacuum. For example, Yoshi, the dinosaur, could be a type of collector because he sticks his tongue out and collects the GOOMBAs as well. So he could have a different implementation of stomping the GOOMBAs. We then parameterize the trait. So this thing up here is called a type constructor. And you can think about it being exactly the same as a constructor that you would use for like a Java class or the normal constructors for an object. Apart from this constructor takes the types. The underscore is the same as you would in pattern matching, which means I don't care what that type is, as long as you give me a type of f, which has a type constructor which takes another type, I don't mind what it is. So those of you who have done lots of functional programming before will recognize that what this is a functor. The functor is basically a thing for mapping over. In ScalaSyd, we have the definition is we have a trait functor that sends an invariant functor, and the method here is an f of a, so a cage. Everywhere you see f here, you can place with the word cage. So you have a cage of something and a function which takes something and turns it into something else, and then gives you back a cage containing that other thing. So this is the functor. So how do you use it? So you could have you create a object which extends functor, you implement the map function in the same way as we had before, and then you can use this cageFunctor.map method to operate on the GOOMBA and stomp. There is a better way, but to use the better way, we have to understand a little bit about type classes. So if you bear with me for a second, we'll give you a quick overview of type classes. So I'll try and give you type classes in about 60 seconds, but it could be a little bit hard. Right, type classes, why? To use type classes, we want to extend existing classes, but we don't want to use inheritance. We don't want to alter the original source, and we want to kind of keep our concerns separate. So imagine we've got a library which we're importing from a third-party jar, and we want to change, and we want to add a method to it. We don't want to download the source file from Git, recompile it, change the methods, and pump something out. We don't want to use inheritance. What we want to do is we want to use these things called type classes, which let us do all that things without breaking those rules which I've just put out. So here's the quick how. You have a type class, you have instances for particular types, and you have interface methods for the API. So the type class is a simple interface. It has in this case, what we're going to do is a protobuf writer. So you give it a value of type A, and it gives you back an array of a byte array back, which is protobuf. You provide implementations for the types that we care about. So, for example, these are concrete implementations of the protobuf writer. So here we have a coin writer and we have a GOOMBA writer. And both of these will serialize those respective objects into protobuf. We then have interfaces of what we expose to clients. There's two ways of doing this. The first way is to create interface objects. So you create a standard object, and you create a method on that object which takes a value of type A. And then you can also add an implicit parameter of a protobuf writer of type A. So what will happen is that it'll look in the context, and it will say, have you got anything in your implicit context which is of a protobuf writer which is parameterized by type A? So it might be coin, or it might be type GOOMBA. So you then import those implicits in, and then we can use this by just calling it with the type coin. The implicit parameter is passed in the background to your method. The other way of doing this is using the implicit class here. So what this does is it takes a value of type A, and it adds a method to that thing of type A. So in this case, the toProtobuf method. And you use this by importing the default implementations and also importing this class here, and magically the coin class then gets the toProtobuf methods. This is kind of like how ScalaZ does it. And this is the reason why we're talking about type classes, is because we want to understand how ScalaZ adds methods to our classes. So here's how ScalaZ does it. It does it a little bit more of a rounder way. So in the Scala language implicit, you have to import this in order to do the implicit conversions. And the first thing you've got is you've got this toProtobuf write-ups. So here we're using the implicit def. We're not using the implicit class, which is different from what I talked to you about before. So what this method does is it returns you a new protobuf writer ops. It wraps your type, the type A, which is coming in here, in a protobuf writer ops, and it adds all those methods to that class implicitly. In ScalaZ, they also have this object here which extends this trait, which is how you bring that implicit definition into scope. And here's our implementation of protobuf writer ops, where we've got a write method and we've got a write base 64 method. So we've actually added, using protobuf writer ops, we're adding extra methods in which consume that write method there. All right, so that's implicits, but careful. I've had to deal with a lot of code, and implicits can be a very powerful thing, but sometimes they can lead you into a lot of problems. Kind of similar to if you're using warp pipes, you can end up in places which you didn't expect to be. So now we understand that, we can look at ScalaZ and see how we get the functor operations onto our cage type, which is where we were trying to get to. So this is the conversion from an implicit functor of f, which is our cage. We have a functor of f, and we have a functor, and we have a class of f of a. So that's our cage containing coins or GOOMBAs. And it returns a new functor ops, which is the operations that we want to perform on the cage. And here's the operation. So we've got the operation here, which is map, which takes us an A of B and returns back an F of B. So it adds this method onto our cage objects. And finally, you have to import your ScalaSyd syntax into it. So that's a lot of processes which you have to get through to start implementing these functors. So here's a cage functor again. You implement the functor trait, and then you import ScalaSyd functor, and now we just do cage.map.stomp, which maps the GOOMBA calls the stomp method and gives us a coin. So the functor laws have to the functor objects have two laws which have to apply. The first one is you have to preserve identity. So if we map identity over the functor should give us back the same original functor as we had in the first place. And the second one is we have to respect composition. So if we take two functions, so function A and function B, and we compose them together to give us a new function, then mapping that new function should be the same as mapping function A followed by function B. You can check if the functor that you've created breaks the laws by using the ScalaSyd properties from ScalaSyd specs 2. So by creating these arbitraries, we're able to check that our functor doesn't break any of the laws. So remember the 3 points which we talked about earlier. Why is this stuff important? The first thing is the abstraction. The function is an abstract concept. The generalization is there's a set of objects that can be mapped over. So we have the abstract concept, and then we have an interface which gives us that generalization. But what about the context? Where does the context become important? So the context is the function the context is the environment that you apply the function in. So the function can behave differently depending on its context. So what we have is previously we had a function which took us from A to B, and now we have a function which takes us from an f of A to an f of B. So what we've done is we've taken a function that couldn't be applied into a context, and we've turned it into something which can be applied in a context. So we had a function which took an A and returned back a B, and now we have a function which takes an f of A and returns an f of B. There's lots more context available. So we can ScalaSyd option, which is effectively the same as the cage which we talked about, is an option for computations that might fail. Lists are also functors. So in lists, we can show here that lists here are also functors, because we can prove that by using the ScalaSyd properties check. And we have the map method here, which implements that thing. Disjunctions, if anyone's come across disjunctions, these are also functors as well, and we can prove that by running this, by applying this to the functor laws. So why is this handy? So ordinary functions are much simpler to write. They're easier to use and they're easier to reason about. But sometimes we want these nice properties that option or lists and that sort of things give us. So functors let us write ordinary functions and then promote those functions into contexts that we might need. As new contexts arise, we just define new functors to promote the functions into those contexts. We don't have to rewrite the original functions themselves. So here we have the final solution to killing the GOOMBA. We have a stomp function. We have a cage. We then promote that into the context, and then we use it. So the ordinary function is in the context. We promote it into the context, and then we're able to use that function. So then we've just finished level 1. The next levels are a lot shorter. So apply lands. The next trait I want to talk about is apply. So in this case, we need to kill a piranha plant. So in our little Mario arsenal at the moment, we've got something which knows how to take a function of A to B and turn that into a function which takes an option and takes a value in a context and returns back a value in a context. But the piranha plant's a little bit different. The piranha plant, you can't stomp. The piranha plant, you have to shoot. So we've got our coin, we've got our fireball, and we've got our piranha plant. What you have to do is you have to shoot the piranha plant with a fireball, and you get back a coin. So let's try our map function. You know, we give it a go. So we get our cage, and we put a piranha plant in it, and we try and shoot it. It doesn't work. The reason it doesn't work is because our new function takes two parameters, not one. So what are we going to do about it? We're going to try and use currying. So currying is the ability to is partial function application. It means we take our function, which takes two parameters, and we turn it into a function which takes a piranha plant and returns back a function that takes back a fireball and a coin. And when you give that function the fireball, it will give you back the coin. So that's currying here. So you can see here we do shoot _.curried. And that gives back a function which takes a piranha plant, returns back a function that takes a fireball and gives us back a coin. So let's try mapping that over the piranha plant. So we try that now. So we map that. And it gives us back a cage that takes a fireball and gives us back a coin. But what happens if our fireball comes from an unreliable function as well? The problem. So in other words, not only is the piranha plant hard to get hold of, the fireball is also hard to get hold of, and the computations might fail, so it might end up getting a null pointer. So we want to take. The problem is the functor only supports mapping functions over a functor, so it only supports taking a f of a and applying an a to a b of it. We need to map a function in a functor over a value in a functor. So here is apply. Apply allows us to take a value in a context and a function in a context and return back a new value in a context. So now we can, if using this here, we can now take a fireball in a context and a piranha plant in a context and apply it to a function. This is the ScalaSyd syntax here. So this is the promotion, and this is the operations which are used. So this is the apply operator here, which calls the apply that you define here. So what does our vacuum look like now with the apply? So it looks like this. We have to have something in both FAB and FA in order to return back a value. Otherwise, we just send back an empty cage. We also have to define the map function here too as well. So how would you use it? So this is how you'd use it. You carry your function into a cage, and you take a piranha plant, and you get back this partial function here. Then you put a fireball on a cage, and you send back the partial shoot function. So now we've got and we get back a coin. If you did a empty cage, you would get back an empty cage because this bit would not get evaluated. So what have we done? We've taken a function that takes two values, and we've turned it into a function that takes two values in a context. Apply have laws as well, as same as Functor does, and we can test those laws again using Scalaz, using the Scala check properties. Options are apply instances. So here's the definition from ScalaSyd of apply from the option. And this is how we would use them. So rather than using cage, we take exactly the same shoot function, and we use the option classes here, and it allows us to apply that function. Take the shoot function and apply it in the context. Here's some nicer syntax. So this syntax here with a hat allows you to not use the carried function because it does it for you. So you just have to put your two values into context. The other one here is the lift method in ScalaSyd. So then you put the function call first, and then you pass in the two options here. Lists are also applies. So here we have 3 piranha plants, and that gives us 3 partially applied functions. And then we apply a fireball to those. We get 3 coins coming out the other end. So we've taken the same function and we put it in different contexts, and it's behaved differently. And also disjunction is an apply as well, and you can use that here. So apply lets you take a function that takes values and turn it into a function that takes values in a context. You write the code once, and then you reuse it in the context that you need. So the apply is the abstract concept. There's a set of objects that implement the apply trait, and how the functions are used depends on the apply specialization that we're using. So what that might be option, list, or either. So that's the end of level 2. Applicative. So in the applicative world, there's these KOOPA troopers. These KOOPA troopers, you have to stomp them, and they lose their wings. Then you stomp them again. So this is a KOOPA paratrooper. You stomp him, he loses his wings. You stomp him, he turns into a shell. And you stomp him, and he turns into a coin. So here's the code for that. So here's our KOOPA paratrooper. Here's the KOOPA trooper. Here's the shell, the coin, and the fireball. We have 3 methods. The first one shoots the paratrooper, so the paratrooper, and he turns into a KOOPA trooper. The next one shoots the KOOPA trooper, and he turns into a shell. And the next one shoots the shell, and he turns into a coin. So based on the apply, we can now use the function apply. So we can use this syntax to get our coin and to collect the coin. There's some applicatives gives us a nicer way of putting objects into a context. So applicative defines this method which takes an A and just lifts it into a context. You can see here how you'd implement it. Here how you'd implement it. So this is apply is the same as the previous one, but here we just take the value A and we put it into a cage. We no longer need to define map, because you can define map via apply and point. So we just have to apply this, and so this is much simpler to write. So here's the code using applicative. We do fireball.point, and we do paratroopa.point, and then we apply the shoot KP function, and we do the same again, and we apply the shoot KT function, and then we do the same again, and we shoot the S function, and we end up with a full cage with a coin. Here's some different here's a different context. Here's using the list context. So we use exactly the same functions, shoot KP and shoot KT, shoot S, and we get back the coin. So in this case, the applicative is the abstraction, and the generalization is the applicative trait, and we get different behaviors for the same code depending on the context we put the function in. So and then on to level 4, which is the final level, which is around monads. So in the final level, we have Bowser. And we have to defeat Bowser. So the rules for defeating Bowser is that Mario can hit Bowser, Bowser can hit Mario, but Mario dies if at any point the number of hits on Mario is greater than the number of hits of Bowser plus 2. So here's our first try. We're going to create a case class, which is called hits. And this is the number of hits Mario's had, and this is the number of hits Bowser's had. We create 2 methods, hit Bowser, and which takes the hits and we copy it, and we add a hit to Bowser, and we hit Mario, and we add ones to the hits in. We add one to the number of hits in Mario. We can now chain together these computations using function composition, so we can hit Mario, and then we can hit Bowser, and then we can hit Bowser, and then we can hit Bowser. And if we pass in, and when we call this function, with 0, 0, we get hits 1, 3. So Mario's been hit once, which is right, and Bowser's been hit 3 times, which is correct. How about this? We hit Mario, then we hit Mario, then we hit Mario. Then we hit Bowser, then we hit Bowser, then we hit Bowser. So that's good. We've got 3 hits to Mario and 3 hits to Bowser. If we hit, and if we call it with, so this is wrong, sorry. I've just copied and pasted that wrong. But in the first example, Mario must have died. Mario should have died, because he's been hit 3 times. And you can only get hit twice more than being hit Bowser. So what we want to do is we want to fail this computation when he gets hit more than 3 times. So how about this? We know that we can fail the computation by using a cage. So here we change our function from hits, which returns a cage. Using this code then, if we work out that Mario's been hit too many times, then we return an empty cage. And in this case, in the same here. So what's the problem? The problem is that these functions both take hits, but they return context. And what we want a function that takes a context and returns a context, because we want to chain these things together. So that's where monad comes in. So what monad allows us to do, if we look at this bind, so monad inherits from bind, and bind gives us the ability to take a f of a and return back and a function of from a to f of b and return back f of b. So if we define a monad for our cage, we define this bind function here, and we match on the incoming f of a. Incoming cage. If it's a full cage, we apply the function. If it's an empty cage, we sort of send back the empty cage, which means this function here will never get applied. The extra function the method we have to define as well is point, which is from our apply class, which we mentioned earlier. So here's the bind ops, which gives us the method. So here's the implicit conversion of bind to bind ops. So anything which has a implicit object gets these methods of flat map and bind. So these two methods are interchangeable. Both flat map and bind are basically the same function definition. So now when we try it, we do cage hits. We send that to hits 2 to hits Mario, and then we hit Mario 3 times, and we hit Bowser 3 times, and we get back an empty cage, which is what we expect because Mario's been hit too many times. And if we start off Bowser being hit 2 times to start with, then Mario doesn't die because the maths works out. So also you'll have used monad in the flat map in the for comprehension. So we can also write it like this. So there's other monads that we can use. So the option is a monad. The list is a monad. There's also a reader monad, a writer monad, and a state monad. There's also laws for monads. So we need the right identity and the left identity laws, which I'm not going to go into now, but you can look them up. But hang on, I can't reuse these functions. I've been saying all the way through that the whole point of this is that I can reuse the functions. So here's my attempt of reusing the function. So if I pass an implicit monad f, now I can use the point function to promote it into a context, and it works like that. So monad lets us take a function that takes a value and returns a value in a context with a value in a context. So the abstraction is the monad, the generalization is the monad trait, and the context is different behaviors for the same code. So in summary, a functor lets you take a function from a to b and change that to a function which takes an f of a and returns an f of b. Apply takes a function from a context which contains a function and apply it to a value in a context. A point applicative lets you just take a value and put it into a context. And bind or flat map allows you to take a value which is in a context and apply it to a function that takes a value and returns a value in a context. So here's the references for this talk. If you're struggling with this stuff, it's probably better. I'd recommend actually looking at the learning Haskell for the greater good, because sometimes the Scala syntax gets a little bit in the way. The Learning ScalaSyd website pages here at this side is good too. Functional programming in Scala is good for learning this stuff too. And then there's also some stuff about category theory on Bartos's blog, which is interesting too. All right, so that's the end.
Excellent. Any questions? Lee? Oh, cool. All right, we'll have a short break and we'll be back with Mark.